Okay, now recording. All right, on paper, I was only supposed to do 6.4. I think I'll be able to finish that today with no problem. So we may finish early today. Let's see. And see, what can I do here? Something kind of messed up here. All right, and 6.4 is the last section we have to cover for next Thursday's test. Okay, so I'm already here. So that means starting tomorrow, I'll give you chapter 7 material, but that will not be covered on the test. Okay, so here's an adjusted schedule. So exam 3 is not going to be this Thursday. It's going to be Thursday the 18th. So that being the case, let's plan for Thursday, this Thursday, 7.2, and the next quiz number 6. Okay, so again, we may finish early today, depending on how far I get with 6.4. Now, tomorrow, 7.1, tomorrow I definitely have to finish early. I've got some business to do fairly early. So tomorrow, what I may do is go up to 12 and a little bit past 12, but there will not be a break per se. I might just continue on to 12:05, 12:10, 12:15, if you don't mind, if you can just hang on that long, and then I'll just dismiss. And then after that, I have to kind of get going. So rather than breaking the usual time and then coming back and lecturing another 10, 15 minutes, if you can just bear with me tomorrow, I'll just go straight through to a little bit past 12. Maybe not even that. If I finish early, then I'll just finish early, and then I'll just dismiss class tomorrow, 12:10ish, 12:15, something like that. Okay. So because I have to get going tomorrow, so tomorrow we'll definitely finish early. Okay. So I'll finish 6.4 tomorrow. I think we'll finish early today, and we definitely will have to finish early tomorrow. So schedule for now, Thursday 7.2 and quiz number 6. Okay. All right, so I'm going to go back and do more of these types of problems that we had yesterday. In fact, I was going to go ahead and show you 3A that we did in class, because some of you got it, some of you had no idea what to do. Okay, so I'll show you that. And then the last type of problem after that are these identities. Okay, and that's what we're going to cover today. So let's go back to 3A, then what did you had? It was the first quadrant, so it's the easiest case scenario. It's harder when you're not in the first quadrant, then you have to figure out what's the sign SIGN of what we have, okay? So let's pretend I never gave you 3A. And if you got it right, great. But some of you said you had some trouble with it. So let's just go back and do it, pretending that we never did it. You say, well, I already did it correctly. Well, good. It would just be a nice review. Okay, so cosine of theta is 5/13. And it said theta is between 0 and 90 degrees. So I'm in quadrant 1. Best case scenario, everything is positive, right? So maybe I'll just put back up this. All students take calculus, okay? Or ACTS, A-C-T-S, if you go this way, or forecast, starting from quadrant 4, C-A-S-T, if you would have memorized it. Okay, so for sine, cosine, and tangent, all of them are positive in quadrant 1. Sine is positive in quadrant 2. That means cosine and tangent are negative. Tangent is positive in quadrant 3. That means sine and cosine are negative. And cosine is positive in quadrant 4. That means sine and tangent are negative. Okay, but here you know everything is positive. Okay, sine squared theta plus cosine squared theta is equal to 1. Okay, cosine theta is 5/13. Plug that in here. Remember, cosine squared theta means this. Okay, that means the same thing as that. Okay, so sine squared theta plus 5/13 squared equals 1. Okay, 5/13 squared is 25 over 169. It's 1. Subtract 25 over 169. Remember, 1 you can pretend is 169 over 169. So 169 minus 25 is 144. Square root, square root. Now, normally when you do the square root, that's where you have to figure out the correct sign, SIGN. We're in quadrant 1. Everything's positive. But let's pretend you were told you're in quadrant number 4, then that means the SIGN of the SINE is negative, then I want the negative. But in this case, I want the positive. So sine of theta, square root of 144 is 12, and square root of 169 is 13. Okay, and once you have this, everything falls into place. Okay, so let me make my little table now. Sine of theta is 12/13. Cosine of theta was 5/13. Okay, tangent is sine over cosine. So that divided by that, and again, go straight to the shortcut. The shortcut is you can just lose the 13s. So 12 over 5. Okay. And then the reciprocals, you just have to know which is the reciprocal of what. So what's the reciprocal of the sine? Hint, there's no co here. So reciprocal has cosecant. And what's the reciprocal of the cosine? I said co, so secant. And tangent, cotangent, most students don't have any trouble with that. So. Okay, so here's a very logical way for you to list your answers. And if you do this, it's easy for me to see too. Then just flip all these, right? So 13 over 12, 13 over 5, and 5 over 12. And that's it. Okay, so that was the in-class assignment. You'll see. Now, if you got it wrong, don't worry about it. It didn't count as a quiz. It's just an in-class assignment. I want you to be able to do some problems sometimes without the pressure of quiz, test, and so on, right? So you got it absolutely wrong. Don't worry about it. You didn't lose any points. Okay. So when I have these in-class assignments, the only way you're going to lose points is if you don't try and you don't submit anything. Okay. Or if I can kind of tell that you're not, trying. So, somebody one time said, oh, Mr. Hum has these in-class assignments. So I don't know what I just put 0. Next day, 0. Next, no matter what the question is, the answer is 0, right? Just automatically put 0 since he's not grading it anyway. Well, I can kind of tell you're not really trying there, right? So if you do that, then I might take off points for participation, right? So again, for these, I don't mind if you get it wrong, but I don't want you to just every day just put 0 automatically, right? No matter what the question is, the answer is 0. Okay, because it's probably going to be 0 sometime. Yeah, it might be 0 sometime, but I want you to at least try them out. Okay. All right. So that's that one. Let me try some other one. How about I'll show you number 7. All right. Secant of B is -3/2. 180 less than theta less than 270. All right, if I'm between 180 and 270 degrees, what quadrant am I? Right, 90, 180, 270, 360. It's quadrant 3. Correct? So you should already be comfortable with 90 degrees, 180, 270, 360. So quadrant 3. What's positive in quadrant 3? Tangent. Sine and cosine are both negative. All right, let's flip it. Reciprocal of the secant, no co. So reciprocal has a cosine. -2/3. All right, sine squared B plus cosine squared B equals 1. Sine squared B plus cosine is -2/3 squared equals 1. And you should know, even if this is positive or negative, when you square, it's going to be positive, right? So -2/3 squared is 4/9. Sine squared of B plus 4/9 equals 1. So subtract 4/9. 1 minus 4/9 is 5/9, right? Okay, 1 minus 4/9 you should be able to recognize quickly that's 9/9 minus 4/9. It's 5/9. Okay, square root, square root. This time I want the negative because the SIGN of the SINE in quadrant 3 is negative. Okay, so sine of B is negative. Square root of 5, you can't do anything, but the square root of 9 is 3. So negative radical 5 over 3. Okay, there we go. And now I can make my chart. So why don't I just go ahead and make the chart just like this. If you want to start with cosine, that's okay. Also good. So sine B, cosine B, tangent B. So let's see, sine negative radical 5 over 3. Cosine of B was negative 2/3. Okay, the tangent, the nice thing about having it like this with sine, cosine, because you know tangent is sine over cosine. So that divided by that, it's positive, negative divided by negative. Again, that divided by that, just drop the 3's. So radical 5 over 2. Okay, again, tangent is sine over cosine. This divided by this, it's positive. And furthermore, we already know we're in quadrant 3, right? So quadrant 3, the tangent should be positive. That confirms it. So that divided by that, drop the 3's, radical 5 over 2. Okay, then the reciprocal of the sine is cosecant. Reciprocal of cosine is secant. Reciprocal of tan is cotan. And flip, flip, flip. So negative 3 over radical 5. And yeah, I don't really care about the rationalized denominator. You can just leave it like that. And flip that, negative 3/2. And flip that, 2 over radical 5. So there we go. All right, now they give you some here where they see 9 and 11 and 13. They don't give you a number, they give you a letter like a U or U over radical 3 or something crazy like that. So how do you do something like that? Okay, well, let's see, 13 is in the first quadrant, so that's the easiest. So 11's harder and 9 is a little bit harder. So that's quadrant 4. I just did a quadrant 3 one, so let me do a quadrant 4 one. Okay, so 9, cosine theta is T over 3. Okay, how do you do that? Cosine theta is T over 3. And number 9, theta is between 270 and 360 degrees. I'm in quadrant 4, right? Okay, 90, 180, 270, 360, quadrant 4. So quadrant 4, which trig function is positive? Cosine. That means sine and tangent are going to be negative. All right, so I just do the same thing as the other ones, except the number's not as nice. Okay, so sine squared theta plus cosine squared theta equals 1. And now I plug in T over 3 for cosine theta right here. So sine squared theta plus T over 3 squared equals 1. Cosine theta is T over 3, so I square it. Remember, cosine squared theta means cosine theta squared. Oops, that should be a plus, not an equal. All right, so I square that, I get T squared over 9, right? Okay, subtract that over. 1 minus T squared over 9. And maybe just to get a nice denominator, multiply by 9 over 9. So sine is, I'm in quadrant 4, so I want the negative of the square root of 9 minus t squared over 9. Okay, common denominator is 9, so I have 9 minus t squared over 9. Do the square root, and I have that. The square root of 9 is 3. So I'm going to write sine of theta is negative radical 9 minus t squared divided by 3. Cosine of theta was t over 3. Tangent. Sine over cosine, that divided by that. Again, just drop the 3's. Looks like I have a negative. So negative radical 9 minus t squared divided by t. Okay, so once again, whenever you divide and you have the same thing top and bottom, which will happen a lot in our class, as I said, just drop it right here. Okay, little timeout over here again. If you ever see A over C divided by B over C, just make it A over B. Just drop the C's. How can you justify that? If you multiply top and bottom by C, then all the C's cancel out. Another way to look at it is if you divide by a fraction, you multiply by the reciprocal. So you would say A over C times C over B, and then the C's cancel out and you have A over B also. All right, and then same stuff. Reciprocal of sine is cosecant, reciprocal of cosine is secant, reciprocal of tangent, cotangent. So cosecant theta, secant theta, cotangent theta. So flip, flip, flip. So negative 3 over radical 9 minus t squared, 3 over t, and negative t over radical 9 minus t squared. And there we go. Okay. All right, I'll show you one more of those, which is 11, and then I'm done with that type of problem. Then the rest of the day, we'll be doing so-called identities. Prove that the left side and the right side are equal. You're not solving those equations, you're just showing that they're the same. Those are called identities in mathematics, where the left-hand side and the right-hand side are the same. I'll show you how to do that. Okay, 11. Sine of theta is negative 3u for 11. Theta is between 180 and 270. So what quadrant are we? 180 and 270. We've already seen that. It's quadrant 3. Okay, so quadrant 3, tangent's positive, sine and cosine are negative. So sine squared theta plus cosine squared theta equals 1. Sine of theta is negative 3u, so negative 3u squared plus cosine squared theta equals 1. Again, sine squared theta means sine theta times sine theta, or sine theta squared. So negative 3u squared is 9u squared plus cosine squared theta equals 1. Subtract 9u squared on both sides. Okay, that's cosine squared. So if I want cosine, I just do square root, square root. I'm in quadrant 3, so the cosine should be negative. So I want the negative. Cosine theta is negative radical 1 minus 9u squared. Sine, cosine, and once you have sine and cosine, everything falls into place. So I'm ready to make my little mini table again. Okay, so Sine of theta was negative 3u. Cosine theta is negative radical 1 minus 9u squared. Tangent theta, well, it's sine over cosine, so that divided by that, just two negatives make a positive, so I'm just going to write 3u over the square root. 3u over radical 1 minus 9u squared. So sine is positive, cosine is positive, sine is negative, cosine is negative, tangent's positive, as it should be in quadrant number 3. And then the reciprocals. Reciprocal of the sine again is the cosecant. So negative 1 over 3u. And reciprocal of cosine is secant. Just negative 1 over that thing. Negative 1 over radical 1 minus 9u squared. Cotangent, just flip this guy. Radical 1 minus 9u squared divided by 3u. And that's it. All right, so I'm done with the 1 through 13 type of problem, and the rest of the time is working on identities. Okay, so you're not solving for the angles in 15 and on. You're trying to prove the left side and the right side are the same thing. Okay, so identities. Okay, so prove left-hand side, hereafter dubbed LHS, equals right-hand side, which I will now rewrite as RHS if the context is clear. Right, so ground rules for an identity. You say something equals something. It's not an equation, okay, where you say, okay, X can only be certain values. You're trying to show that it works all the time wherever the value is defined. Okay, so there's certain rules that you have to apply for that, and I'll tell you what the rules are. Okay, so number 15. Sine of theta, cosine theta, secant theta, cosecant theta equals 1. Okay, first rule that I want you to apply, and by the way, if you get different teachers are going to have you solve identities in a different fashion perhaps, okay? But since I'm your teacher, you got to do my way. Okay, some of you have some background in trig. You say, my previous trig teacher did this. That's fine, but I'm your teacher now. You got to do it my way, okay? All right, so wherever the equal sign is, put a little barrier here. But there's a reason for that. Okay, you're not supposed to cross this barrier. Don't cross the barrier until left-hand side equals the right-hand side. You have to get this to match this exactly. So some of the rules that you had before when solving equations don't apply, meaning you're not allowed to multiply both sides by 2, let's say. You can't take the square root of both sides, okay? You can't divide both sides by 3. Those are not allowed, okay? There's an impenetrable barrier, so to speak. So you work on this side, you can independently work on this side, and your goal is to try to get the 2 to match. And only when the 2 match can you sort of cut across. Now in this particular case, there's nothing to do on the right side. 1's about as good as it gets. We just leave 1 as 1, okay? But wherever the equal sign is, put a barrier, you don't cross it. So that means multiplying by 2 is not allowed on both sides. Okay. We have to prove they're equal. We're not assuming they're equal. We have to prove they're equal. Okay. So let me show you what to do in this case. Usually it's a good idea when you have the reciprocal functions to write them in terms of sine and cosine. And that's pretty much it. In fact, that's going to work in this particular case. So on the left-hand side only, sine theta, cosine theta, secant theta. What is secant? It's 1 over the cosine. What is cosecant? 1 over the sine of theta. And no big surprise, gone, 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 gone. So the first example is maybe too easy, so I get 1. And now that they're equal, I can cut across and say that the left-hand side and the right-hand side are equal. Okay, I never assumed that they were equal. Okay. See, when you have an equation, like if you say, so quick timeout, you don't have to write this if you don't want to. 3x equals 6, something very easy. Divide by 3, right? X equals 2. You're solving for x. So you're making the assumption the left side and the right side are equal. So that allows you to say if two things are equal, then when I divide both sides by 3, they're equal. Okay, that game doesn't apply here. Okay, you are not assuming they're equal. You have to prove that they're equal. So if you're proving they're equal, you cannot assume they're equal, which means a step like this: divide both sides by 3, square both sides, take the logarithm of both sides or whatever. Those are not allowed. Okay, I can work on this side. I can work on this side all by themselves. And then when I finally get up the match, then I can cut across, so to speak. Okay, now this first example is pretty straightforward. There wasn't any algebra to do here. So maybe the next ones that I'll show you are a little bit tougher, perhaps. Okay. So let me try 19, where it is a little bit harder on both sides. One minus 5 sine x over cosine x equals secant x minus 5 tangent x. Okay, so when you're solving identities, I want you to immediately put a barrier aligned. Okay, that's to remind you, you can't do the same thing, quote unquote, on both sides. Just like when I'm solving 3x equals 6, say, oh yeah, divide by 3, x equals 2. That's not allowed by the rules of the game here. So for instance, I might say, oh, I don't like the fraction. Let me multiply both sides by cosine x. That's not allowed. Okay, I am allowed to work on this side separately. I am allowed to work on this side separately. Okay, but I can't cut across until they're exactly equal. All right, so how do I proceed? Let me try to work on this one. Okay, so on the right side, I don't like secant. I usually don't like secant, cosecant, cotangent. I'd rather have sine, cosine, and tangent. In fact, whenever I can get rid of tangent and just do sines and cosines, that's a good idea. So when solving these identities, if you can ever just get it to be in terms of sine and cosine, just sine and cosine, then that's usually the way to go. So, you know, I don't want all these secants and cotangents and tangents all over. You're allowed, one trick you can always try is to change everything to sine and cosine. Makes it a little bit easier. All right, what is secant? 1 over cosine x minus 5. What's another way to write tangent x? Sine x over cosine x. Aha. And what do I notice? I have a common denominator here, which allows me to write the right-hand side as this. And lo and behold, they are equal. Okay, so that's the game that we're playing. Notice in this one, I only worked on the left side. Well, to me, it was kind of obvious. 1, there's nothing to do with 1. That's already as good as it gets. Okay. On this side, it looks like I only worked on the right-hand side. You have a choice. You can either work on the left side or the right side. You might have to end up working on both. Okay. The only thing you cannot do is cut across or do the same thing to both sides, like multiply by 3 or square both sides. That's not allowed. Okay. All right, so this is what we have for identities. Okay, and just show you some more of these. How about I show you 23? One minus sine theta, secant theta plus tangent theta equals cosine theta. Okay, so I separate. Can you guess which side I'm going to work on? There's really nothing to do here, right? What are you going to do with that? So it looks like I'm going to multiply this out. So what strategy? How about I'll FOIL it out and then I'll change everything to sine and cosine, and maybe that tells me what to do, right? So I'll FOIL this out first, outer, inner, last, and hopefully I get cosine theta. So equals secant theta plus tangent theta minus sine theta secant theta minus sine theta tangent theta. Right, yeah, let me raise it up. Go back to here, raise that up so you can see a little bit better. I want to catch out on the video. Yeah, maybe I should have done that on the other side too, sorry. Okay, so I'll quickly raise this up if you want to look at the video later if it wasn't clear enough. And you can always pause the video and go forward and backward as necessary. Okay. All right, now how can I possibly get that to look like that? Let's change everything to sines and cosines and maybe that'll help me, right? So secant is the reciprocal of the cosine. Tangent is what over what? Sine over cosine. Let's see. Sine theta. Secant is the reciprocal of the cosine. I can write it like that. Sine theta. Tangent, sine over cosine. All of these have a common denominator. That means I can combine them. In fact, take a look at this. Right? Sine theta over cosine theta minus sine theta over cosine theta. It's nice. Okay, how do I get that to look like that? Okay. 1 minus sine squared theta. Okay, so quick timeout here. The book went over this also, but sine squared theta plus cosine squared theta is equal to 1. So if I subtract one of them to the other side, I have sine squared theta is 1 minus cosine squared theta. if I subtract cosine squared theta on both sides. Similarly, I could have cosine squared theta is equal to 1 minus sine squared theta, right? 1 minus sine squared theta, cosine squared theta. And there we go. Right, so you want to get comfortable with this one for sure. If sine squared theta plus cosine squared theta equals 1, that means sine squared theta is 1 minus cosine squared theta, and likewise cosine squared theta is 1 minus sine squared theta. And yeah, now you just cancel one of the cosines out. And so you have cosine theta. I can cut across and say that they're equal now. Okay. All right. So number 1, sine squared theta plus cosine squared theta equals 1. Put that in your cheat sheet. Now, it's up to you if you want to put these on your cheat sheet or not. They follow directly. Okay, it's just some simple algebra. But that's a hint. Whenever you see 1 minus cosine squared or 1 minus sine squared, you can always change it to this. If you need it, it looks like we needed it. So there we go. Okay. All right. Do some more for you. How about 25? And tell you what, if I do 25, let me start up here. Otherwise, I think I'm going to run out of room. Secant alpha minus tangent alpha squared equals 1 minus sine alpha over 1 plus sine alpha. Okay, this is alpha. Alpha, beta, gamma. After a while, like I said, you get to know the Greek alphabet. All right. Draw myself the impenetrable barrier, so to speak. So what I'm not allowed to do, take the square root of both sides, as much as I want to do that, for instance. Okay, you have to work on this side independent from this side. Okay, which means, what am I going to do? Well, I don't know. Maybe let's just square this first. So I will square this binomial, secant squared alpha minus 2 secant alpha tangent alpha plus tangent squared alpha. Right now, I have no idea what to do with this, so we'll just leave it alone. Okay. This one, remember, that's a square of a binomial. And maybe I'll sneak in another little sidebar here. I'm employing here a minus b squared is a squared minus 2ab plus b squared, right? So secant squared alpha minus 2ab minus 2 secant alpha tangent alpha plus tangent squared alpha. Okay, now what? Now let's change everything to sine and cosine again. So secant is reciprocal of the cosine, 1 over cosine squared alpha minus 2. Secant is 1 over cosine alpha. Tangent is sine over cosine. Plus tangent squared, sine squared over cosine squared alpha, right? And what do you notice on the bottom? There's a common denominator of cosine squared, right? Cosine squared alpha. So 1 minus 2 sine alpha plus sine squared alpha. 1 minus 2 sine alpha plus sine squared alpha. Now, what am I going to do with that? Okay, I notice this happens to be a perfect square. Okay, so this is kind of sneaky where you look at both sides. It's definitely harder. Sine squared alpha minus 2 sine alpha plus 1. That's factorable, is it not? That's sine alpha minus 1 squared. Sine squared minus 2 sine alpha plus 1. And I square it, so I get cosine squared alpha. Okay, how do I compare that with what I have over here? So where can I go from here? It's almost like you force this to be the way we want it. I have 1 minus sine alpha. I have sine alpha minus 1. So on this side, so we're not doing the same thing to both sides. This is definitely a little bit harder. Okay, but I notice I need to get this to be sine of alpha minus 1, which is the same as 1 minus sine alpha squared. So I'm going to multiply by 1 minus sine alpha, 1 minus sine alpha on the right-hand side. So this is our first example where I have to do the same thing on both sides of here. And I'm working on the left and the right, in other words. Okay, I'm working on the left side and also the right side. So if I multiply all this stuff out, you do get 1 minus 2 sine alpha plus sine squared alpha, which is what I have here. The bottom is a difference of two squares. It's like a plus b, a minus b. So it's a squared minus b squared, right? So it's 1 minus sine squared alpha. And there it is. 1 minus sine squared cosine squared. It's definitely a harder problem. So cosine squared alpha over 1 minus sine squared alpha. And yeah, I can now cut across. Oops. I didn't want that, sorry. I want this thing. 1 minus 2 sine alpha plus sine squared alpha over 1 minus cosine squared alpha. There we go. That's what I want. I'm supposed to leave the top alone, change that to cosine squared. Okay, so now there we are. These are the same. So it's our first example where I work on both sides. Definitely a harder problem. Okay, folks, I think we'll break for now. I'm actually not that far from finishing 6.4. So maybe what I'll do is I'll do 6.4 and I'll sneak in a little of 6.5. That'll just make it easier for me to finish tomorrow, since I have to finish early tomorrow anyway. Okay, so rather than finish real early today, we'll finish somewhat early today and definitely early tomorrow too, okay? All right, so we'll take a break right now until 12:10 as usual, yes, okay? So break until 12:10. Okay, folks, I'll do some more of these identities, then I'll be done. I'll maybe sneak in a little bit of the next section, but then we'll end somewhat early, hopefully. All right, so let's see. Let's try something like a 27. That looks pretty bad. Sine A plus cosine A equals sine A over 1 minus cotangent A minus cosine A divided by tan A minus 1. Looks like a big mess. Looks like most of the work is going to be on the right side. Cosine A over tangent A plus 1. All right, I mean, you look at this and say, how do you know what to do? Sometimes you don't know what to do. Let me just immediately change everything to sine and cosine. Maybe that's a good way to start. So even though I'm going to have a fraction inside a fraction, there's nothing else to try. And it looks like there's nothing to do on the left side. Let me make sure I wrote it correctly. Yeah, okay. So sine A over 1 minus, okay, cotangent is cosine over sine. Cosine over, tangent is sine over cosine. Okay, so right now I have this. So what can we do? How about, let's get rid of this weird looking stuff. So on this side, get rid of the complex fraction. Let's multiply the numerator and denominator by sine of A. Sine A over sine A. And this one, how about cosine A over cosine A? So this gives me sine squared A over sine A minus cosine A. And this is cosine squared A over, let's see, sine A plus cosine A. Now, I do not have a common denominator. Sine A minus cosine A, sine A plus cosine A. And check something else here. Sine A plus cosine A. Make sure.
It's tangent A minus 1.
Tangent A minus 1. That's probably what the trouble is. Thank you. So that's why it wasn't working out. So sorry, that's a minus. That's a minus. That's a minus. Ah, now everything clicks. Sorry. Minus, minus. Okay, so I indeed do have a common denominator. That's the key. Okay, there we go. Sine squared A minus cosine squared A over sine A minus cosine A. And yeah, I notice this doesn't have any denominator. So how about on this side, I just multiply by sine A minus cosine A top and bottom, and that should do it. So in other words, sine A plus cosine A. It's almost like saying, what do I need in the bottom? I need that, so I'll just put it. Sine A minus cosine A, sine A minus cosine A, like that. Be kind of hard to read. Okay, sine A plus cosine A, sine A minus cosine A divided by sine A minus cosine A. And why did I do that step? Because I needed to have sine A minus cosine A in the bottom. That told me what to do. And then if I multiply that out, I get the numerator, so it finally works. So sine squared A minus cosine squared A divided by sine A minus cosine A. And finally, I got them to be the same. Okay, so I messed up over here, but these are all minuses. It's a minus there. Okay. All right. Okay, maybe just one more like that, and that'll do it. How about 33? Looks like a pretty bad one. Cotangent squared A plus cosecant squared A equals negative cotangent to the fourth A plus cosecant to the fourth of A. Cotangent squared A, cosecant squared A. Yeah, let me make sure I wrote it correctly this time. Okay, so how can I do anything until I change everything to sine and cosine, maybe? Okay, so cotangent is cosine over sine. Cosecant is 1 over the sine. So sine squared A. This is cosine over sine to the fourth power. And cosecant is 1 over the sine. Well, at least I had a common denominator here and a common denominator here. So that's nice. So I'll write this as cosine squared A plus 1 over sine squared A. This one is 1 minus cosine to the fourth A over sine to the fourth A. This is a difference of squares. So 1 plus cosine squared, 1 minus cosine squared. 1 plus cosine squared A, 1 minus cosine squared A. Okay, I can see what's going to happen now. 1 minus cosine squared A. 1 minus cosine squared, sine squared. 1 plus cosine squared A, sine squared A, divided by sine to the fourth of A. And yes, sine squared divided by sine to the fourth, you would cancel, leaving you with a sine squared in the bottom. So 1 plus cosine squared A over sine squared A. These are the same. You don't have to reverse this. Cosine squared A plus 1, 1 plus cosine squared A, we know they're the same. So there it is. We got them to match. All right, so this is how identities work. I did a whole bunch of them for you. You try the rest. I'm actually finished with what I was scheduled to do. 6.4. Okay, so I'll sneak in very little of 7.1 and then I will stop right after that. Okay. So coverage for the exam will be right up to here. So up to 6.4. So again, that's not until, I'm going to mark this off now. That's not until a week from Thursday. So from here until next Wednesday, I'll go on to do more stuff, but anything I'll say from here on out will not be covered on next Thursday's exam, right? Okay, so I'll do very little of 7.1 and then I'll quit. Okay, so still trig. Okay, 7.1 is on something called radian measure. Okay, so it's another way to measure angles. Now, you're all comfortable with degrees, hopefully. Okay, but now we want to learn a different technique of measuring called radians. Now, there's more than one way to measure distances, right? We have a lot of ways to measure distances, right? We have inches, feet, miles, yards, and metric. We have centimeters, millimeters, kilometers, meters, right? Okay, so likewise, there's more than one way to measure angles. So we're already comfortable with degrees. Okay, so if I go degrees, okay, on my calculator, you can see there's a way to change things to radians. So there's radians. So we're going to learn the radian method. I alluded to it a little bit earlier. Okay. On this calculator, there's DRG, which stands for degrees, radians, and gradients. We're not going to fool around with gradients. Okay. But right now I'm in degree mode. So if I'm going to switch, push this, now it's in rad, R-A-D for radian. And there's gradient, which we're not going to use, but it's another way to measure angles. Hit it again and I'm back to degrees. Okay, so degrees, radians, and gradients. Okay, so what is radian measure? The easiest definition I can give you is over here. First, some familiarity that you should already know. For standard position, 0 is considered to the right and counterclockwise is considered positive. Okay, here's the vertex. So this is my theta. Okay, so they give you some pictures. Where am I? On page 468. Standard position starting here. So 30, positive 30, 60, 90, 150, 180, 270, and so on, right? Okay, what is this radian stuff? Okay, now you can look at all the arguments that they have over there. I'll just give you the easiest definition. On page 470, 180 degrees is pi radians. Okay, at first glance, you say that is such a strange way to define it. Okay, but in retrospect, this is actually the most natural way to define it. Okay, when you stop and think about it, 180 degrees, 360 degrees, those are made up numbers. Those are numbers just because they're nice, but pi is useful because it's a property of the circle itself. Okay, so you want to put this on your next cheat sheet, which will not be on this test. It'll be the test after this, but 180 degrees is pi radians. I'll just mention quickly, why do we have such a strange definition? Okay, so let me show you. So 0 degrees, 90, 180, 270, 360. Okay, now the book said 180 degrees is pi radians. Okay, I will superscript radians with an R, but if you don't put anything, like you just leave it alone, it's understood to be in radians. Okay, so R is radians. So later on, if it just says pi, you know it's not degrees, it's radians. 180 degrees is pi radians. Now, why have it like that? Well, let's see. If this is 180 degrees, and that's pi, if I go to 360, that'll be how much? 2 pi radians, right? So 0 degrees is obviously the same as 0 radians. Okay, 180 degrees is pi radians. How about 90 degrees? Half of that. So half of pi, we normally say pi over 2 radians. Okay, so 0 degrees is 0 radians. 90 degrees is pi over 2 radians. 180 degrees is pi radians. If I go all the way around once, that's 2 pi radians. How about 270? Well, that's halfway between here and here. So it's halfway between pi and 2 pi. Well, 1.5 pi. The way we normally write that, though, is 3 pi over 2 radians. Okay, so here are the radian measures for 90-degree multiples that you want to get comfortable with. So you have 0 degrees, 90, 180, 270, 360. Radians go pi over 2, pi, 3 pi over 2, 2 pi. Quick explanation, why do we have such a strange measure? Okay. You might recall there's a formula for the circumference of a circle, 2 pi r, right? If I walk all the way around a circle, circumference is 2 pi r. On a unit circle means the radius is 1. Right? Which means circumference is 2 pi 1, which is 2 pi. Okay, if I walk all the way around a unit circle, I've walked 2 pi units. From this definition, if I go all the way around a circle, it's also 2 pi radians. What that means is that the angle matches the distance that I walk. Okay. The angle matches the arc length in radians. So it's a property of the circle itself, okay, not of an arbitrary made up system. I'm not against it. I mean, 360 degrees, that's a nice number. Okay. It's better than picking something like 521 degrees because, you know, it's hard to split that up. Now, why do we use 360 degrees? It's easy to divide by 2, by 3, by 4, by 5, by 6, by 8, by 9, by 10, right? Okay. But it's otherwise a made up number. Why the 2 pi? Okay, if I go around a circle, the unit circle, I've walked 2 pi units. The angle is also 2 pi. That means the distance that I walk matches the arc length. So it's a property of the circle itself. So that means if I walk exactly 1 unit, that's considered 1 radian on a unit circle. If I walk 2 units, actual distance now, I've gone 2 radians. If I go all the way around a circle, that's 2 pi units. The angle is also 2 pi. So we're going to have the angle match the distance around as an arc length. Okay. Now, if you didn't understand any of this, the only thing you really need to know is 180 degrees is pi radians, and put this on your next cheat sheet. 180 degrees is pi radians. Okay, and that's really all I was going to do. You can put this on your cheat sheet if you want, although I'll teach you how you can get around it. To convert from one to the other, from degrees to radians, multiplied by pi over 180. The other way, from radians to degrees, 180 over pi. You don't really have to put that down. I'll show you when you actually do the conversion, you know, what to do for figuring this out. Okay, so where we're headed, and then I'm just about done. Okay, you have some degree measures changed into radians. You have some radian measures. You can tell it's radians when they have all those pi's changed into degrees. Okay, so we'll be doing some of that. Okay. Then something else that you want to put down, and then I'll be finished. Formula for arc length. Okay, so I mentioned that if you have a unit circle, okay, that means radius is 1, then the angle exactly measures the arc length. Now, what if you have a radius bigger than 1? Here's the formula for arc length. S equals R theta. Okay, so that can be on your next formula sheet, not for this coming test, but the one afterwards. It's on page 472. Arc length S is R theta, but you have to be sure that theta is in radians, not in degrees, in order for the formula to work. S equals R theta. So to find this arc length, multiply the radius by theta in radians. Okay, which kind of makes sense proportionally. If you have a proportionally bigger circle, then the arc length is going to be bigger. How much bigger? Well, it depends how big the radius is. Okay, and yeah, that's actually a direct result of circumference being 2 pi r. Okay, and then this formula for the area of a sector on page 473, sort of like a piece of pie, piece of the cake. You cut that out. Okay, how much is that area? It's a fraction of the whole circle. So there we go. Area is 1/2 r squared theta, but again, theta has to be in radians. Theta in radians there. Area is 1/2 r squared theta. All right, and that'll be the business starting tomorrow, but otherwise I'm done. Okay, so we're gonna stop here. If anybody has a question, you can ask it now. Otherwise, we're just gonna call it a day. Okay, so I'll wait for a moment. Okay, anything else? I'm checking the chat. Okay, otherwise we're done. All right, so that'll be it for today, folks. So everybody have a good day, and we'll see you next time. Okay, all right, bye everybody. Have a good day.
Thank you, Professor. Have a great day.
Thank you. You have a good day.